Okay, welcome everyone. Again, today's webinar, Low E Storms, the next big thing to window retrofits. I'm Pam Cole. I'm a research scientist with the Pacific Northwest National Laboratory. I'm just going to give an intro to Building America. I've been working on the Building Energy Codes program at P&L for the last 14 years, and I'm currently involved in Building America's efforts to resolve code and standard barriers with new innovations. I also help with the technical support for building energy codes across the U.S., answering questions on energy code compliance and how to show compliance for residential and commercial buildings. So an overview of Building America. There's actually 10 supported industry research teams and 4 national labs. And each of these teams and lab partners with dozens of industry professionals, develop and improve systems for residential homes. That is the big, most important part of what Building America does. The best and the brightest in residential building industry can be found here, and we're lucky that we have some of the best and most knowledgeable people and teams on this Building America program with us today. So what does Building America develop? And we're going to talk about low E storms today, but Building America uses applied research, to deliver building science solutions. And they use it in a 4-step type framework. And these innovation solutions are tested in homes and develop proven case studies of successes. And they market those, and they can pinpoint to certain solutions and best practices. Building America provides tools to residential building industry needs, and they ensure the innovations are applied correctly. There's always keeping an eye on energy performance, durability, quality, and actual affordability. And the final step of Building America's process is infrastructure development. And this is the conduit to getting these innovations to the actual marketplace. And so, Building America, what do we achieve? In nearly 20 years of Building America research, we have spearheaded combining ultra-high efficiency and high performance. And this is in both new and existing homes. And we consistently are achieving these challenging tasks. And they're growing every year. And with that, we look at where we've been and where we're going. And for example, in 1995, a home used about 3 times more energy per square foot compared to today. And the indoor and air quality and the comfort and the durability problems, they were common way back in 1995. But today, a home built to DOE Zero Energy Ready homes, the specifications for that uses less than half that energy and is more comfortable, healthy, and durable. By 2030, though, the future, what do we hold for the future? Building America will demonstrate that new and existing homes can produce more energy than they use. That is the goal. So with window retrofit opportunities, it's probably, it's not a mystery to anyone that here on the line that windows are a major source of heating losses. We know this, and the gains in the building, and can significantly drive up residential energy bills. So despite this fact, there's approximately 40% of the U.S. homes that still have single-pane windows. And in homes, the inherently inefficient and they're poor insulators. And we have several case studies that have shown this. The presence of single-pane windows in homes, they have persisted over the past 2 decades. And despite the fact that approximately 30 million windows are replaced each year with higher-performing insulated windows, in addition, almost half, a large percentage of the double-pane windows are not higher-performing low-E windows, but are made of clear glass. So thus there is a tremendous opportunity here for technologies that improve existing windows' performance, such as low-E storm windows, to provide energy savings to a large segment of residences, most of which, accommodate moderate and low-income households. So cost-effective window retrofits, that's always the big question. Are they cost-effective? DOE has supporting, the technology development, market assessments, and early deployment activities of low-E storm windows, which include the recent climate-based modeling effort to determine where and what types of low-E storm windows are cost-effective throughout the U.S. The results are pretty impressive. demonstrating significant savings and, a wide range of climate conditions which can be achieved cost effectively and in most regions throughout the U.S., which is shown here in the climate zone map. Tom Culp, he's our first presenter. He'll talk more in detail about some of these climate-based modeling results. So, a new look at low E storms inside and out. Considering that the amount of energy lost through windows of existing homes each year, this is definitely a remodeling retrofit area, and there is a need for a solution. And although there's a lot of many good window replacement technologies available to homeowners, window replacement is just simply not an option for many homeowners. And for a number of reasons, including cost and affordability, as well as the aesthetic reasons, for some homeowners who want to preserve that historic look of the home. So one of the points that we'd like to emphasize during this webinar is that storm windows have evolved through the years. And there are a lot of people who have an idea about what a storm window is, but these ideas may very well be dated, especially the look of them. Modern storm windows, they're not your grandmother's storm windows anymore, which had to be installed and removed every season, had to be cleaned, almost monthly. Modern storm windows and interior panels are designed to blend in with the existing architecture. Be permanently mounted and are available as both a fixed and operable window. The photo on the left, the interior low E panel, both fixed and operable, shows this. And the photo on the right shows an operable exterior low E storm, which also includes an insect screen. So let me get into the actual presentation, and I'm going to introduce Tom Culp, who has been working with various programs in low E storm windows for over 8 years now. He has headed a DOE-funded research project from 2009 to 2013 to demonstrate through residential and commercial case studies the ability for low E storm windows and retrofit panels to cost-effectively reduce energy costs in existing buildings. He's the owner of Birch Point Consulting, and he'll be providing an overview of the technology for today's webinar, how it was developed, how it works, and he'll be telling us some about the field tests, the case studies, and other research deployment efforts related to low E storms. So Tom, I'm going to let you go ahead and take it away.
All right, thanks Pam. Hopefully you can hear me okay. Yeah, so the technology in low E storm windows has really been under development for almost 15 years now, and it initially started through the Emerging Technologies program at DOE. And DOE supported the national labs to do a lot of testing of the initial concept, starting off with lab testing, going up to some demonstration field case studies, and I'll be talking about some of those areas. And then after this technology graduated from the Emerging Technologies program, it was passed to the Building America program for in-field testing, installation guidance development, and now multiple groups are working on market transformation to make the broader building, energy efficiency, and utility communities aware of the benefits and opportunity for this technology. But I'll start off talking about the initial concept behind low E storm windows and some of the testing that has gone into its development. So really, back in the 90s, Lawrence Berkeley National Lab, LBNL, first suggested this concept that a durable low E glass coating that you would normally think about in a new window could be incorporated into modern storm window designs to create a cost-effective insulating and sealing measure for existing windows. So really, you don't necessarily think about this as a separate window. Think of it as a way or a measure or a tool to improve your existing window. Now, of course, if your existing window is degraded and needs replacement, then you should replace it and do it with the best window possible. But practically speaking, this is not an option for many home and building owners, either because of cost, historic preservation concerns, or that the existing window is fine and simply does not need to be replaced, but you still want to upgrade its performance. In that case, low E storm windows and panels are an ideal choice to upgrade your existing windows at a much lower cost. And it really does this in three different ways. First, it provides air sealing of the primary window. I'll talk about some of the case studies that have shown you see a 10% reduction in the overall home air leakage when you add a storm window. That's not just the window itself, that's of the overall home, because particularly in many of these older existing homes, and particularly with single glazed windows, that's a primary leakage point. So addressing that area can have a significant impact. Next, a Lowy storm window creates a dead airspace that reduces conduction and convective heat losses across the primary window. And then third, the Lowy glass reflects the radiant heat back into the home, so it reduces radiant heat loss, just as it would in a same way that Lowy glass outperforms regular glass in a new window. So this concept, probably the best way to see it visually is visually through infrared field images. This particular image was taken in the wintertime from the outside of a home. So light colors show heat loss and dark colors show where it's more insulating. And in the center there you can see the kind of, the bright original single pane window with a considerable heat loss. And then on either side, left and right, there are operable windows there that have been retrofitted with Lowy storm windows. And you can see side by side how the Lowy storm window is reducing significantly the heat loss through that window. So to test the concepts, kind of going through a little bit of the history, first in 2000 to 2002, Lawrence Berkeley National Lab used their mobile window test facility, or MOIT facility, where they can do side-by-side detailed testing of different window options. And there's a lot more in this study there from Joe Klims that you can look up, but basically they demonstrated that a Lowy storm window plus a single pane primary window performed essentially the same as a new double pane Lowy replacement window. Additionally, a little bit later on, LB&L did some work with Building Green, Peter Yost's group up in Vermont, doing some infrared imaging. And this particular slide here shows on a Vermont winter night an image taken from the interior. So in this case, the dark colors show heat loss, and the bright colors show more insulating performance. And on the left there, you can see an interior Lowy panel over a vintage single pane wood frame window. And on the right, the single pane sashes were replaced with dual glazed Lowy argon sash inserts. And you can see just visually from a heat loss they perform similarly. So the concept, both in lab testing, really looks quite positive that we can get significant improvement in performance by using both interior and exterior panels. So DOE wanted to take the next step and say, well, how does this work in the real world in field studies? So between 2003 and 2006, a field study was done in the Chicago area, co-funded by DOE and HUD, where the primary researcher was NAHB Research Center. Now I think they're called Home Innovation Research Labs now, where they did monitoring on 6 weatherization homes in the Chicago area that had single glazing that were then retrofitted with Lowy exterior storm windows. And this study showed that the heating load was reduced by 21%, and this payback period, a simple payback period of approximately 4.5 years for the Lowy storm windows. Of course, in replacement windows, the payback period is considerably longer than that. Additionally, when doing blower door tests, the overall home air leakage was reduced by about 7%. That's for the overall home, not just the window, so that's actually fairly significant. Following up on this, Chicago's obviously a very cold climate. We wanted to do a similar study in a more mixed climate. So I participated in also a DOE-funded study between 2011 and 2013, again with the NHB Research Center as well as Larson Manufacturing and Quanta Panel, where we took 10 older homes in the Atlanta area that had single glazing and tested different storm window technologies on there. And the Lowy storm windows showed over a 2-year period approximately 15% heating savings, and then as well as 2 to 30% cooling savings. Now you can see there's large variability, particularly on the cooling side, and that's because these are real-life field studies, variations between the homes, the amount of trees around them, and there are real people living in there. These are occupied homes, so there's a lot of variability, but very positive results in general, both on the heating and cooling side. A little bit later on, Sarah Witter from PNNL will talk about the test studies done in the PNNL test homes, which are a more controlled environment. On the air leakage standpoint, in this case, these homes and these single-pane windows were particularly leaky, and so by adding the storm windows, we were able to reduce the overall home air leakage by 17% just by introducing these modern-style low-E storm windows. In addition to the energy efficiency, we also polled the occupants on the other benefits, and in fact, they ranked these higher than the energy efficiency because they are what you notice when you live in the home. And the number one benefit that was cited was the improved home appearance. So like Pam was saying, these are not your grandmother's old storm windows that have to be taken off seasonally and old and clunky. These are designed to be aesthetically pleasing, fit in with the architecture, and improve the curb appeal and dress up these old existing windows. Additionally, reduced drafts, improved comfort sitting near the windows, as well as reduced noise were significant benefits cited by the occupants. In addition to single-family homes, we also wanted to test out low-E storm windows in multifamily buildings. And so part of this same research study with NHB Research Center, Quantapanel, and Larson Manufacturing, we took two older, these are 50-year-old large apartment buildings in the Philadelphia area. Just one of the two buildings is shown here. They're both identical, 101 apartments overall. And these had single-pane metal windows that already had old clear storm windows. But the old clear storm windows were really poor quality, and so we replaced the old clear storm windows with new modern low-E storm windows. And just by replacing those, we saw over a year period, we saw 18 to 22% reduced heating energy use, as well as 9% reduced cooling energy use, so very significant. And we also did the air leakage testing on select apartments and showed that the apartment air leakage was reduced by 10%, which is consistent with the other studies. So very positive results in both single-family homes and apartment buildings. I did want to mention, though, that low-E storm windows and panels are not just for low-income weatherization homes. Obviously, that's one of the first targets, but they're really appropriate and a good window retrofit option in almost any building type where it's either impractical or too expensive or undesirable to replace the existing windows. Of course, if you're going to replace the windows, put in as good of a window as you can, but in many cases, it's just not practical or cost-effective to do so. And in that case, low-E storm windows are a very good option. And as shown here on this slide, this includes homes of all types, historic buildings, light commercial buildings, and even large buildings. All the pictures here show real-life examples where either low-E exterior or low-E interior panels are being used. So, although they're really applicable to almost any building type, of course, one of the first targets when we started to look at this is weatherization, both official government weatherization programs, but also the general kind of weatherization market for upgrading existing homes. So back in 2009, the ability to include low-E storm windows was added to NEAT, the National Energy Audit Tool, and weatherization assistance software, and this is a software used by many state weatherization programs. And then the following year, with DOE support, low-E storm windows were added to Pennsylvania's weatherization measure priority list for single-family homes. And this was the result of a needs analysis for 37 home types, just covering all different home types in 4 different cities across Pennsylvania to cover the different subclimate zones. In this case, the key output we're looking at is the SIR, or savings to investment ratio. And under weatherization programs, the SIR must be greater than 1 to qualify for that program. When we did the need analysis, the SIR was between 1.4 to 2.2 for low-E storm windows over single-pane windows. It ranged from 1.3 to 2.1 over metal frame dual pane windows. And the main study was done for natural gas heated homes, but when you use either propane fuel or electrical resistance heating, then the SI was much higher than this even. So in all cases, it was proven to be cost effective for the weatherization program in Pennsylvania, and they added it to their weatherization measure priority list. So we wanted to, together with PNNL, expand upon this, what was done in Pennsylvania, to do a similar type analysis, but for the entire country. And so we expanded this need analysis. I think we used 39 different home types in 22 cities across all 8 climate zones that cover the U.S., the continental U.S. There's a lot that went into this study. You can download this from the PNNL website, and the reference will be at the end of the presentation or when you download the slides later. But this slide shows one of the key, I guess, conclusions that came out of the cost-effective analysis. In addition to NEAT, we also did some ResFin analysis, which is a DOE2-based program that many of you may be familiar with, to confirm and showed similar results. So this map basically shows that for low-E storm windows and interior panels installed over all single pane windows as well as all double pane metal frame windows with clear glass, they were cost effective in climate zones 3 through 8, which is basically from that blue line northwards, where the SIR ranged from 1.2 to 3.2. In climate zone 3, between the blue and the green line, solar control low-E storm windows are recommended, and above that line, the normal low-E storm windows are recommended. We also did the test over double pane wood or vinyl frame windows, which then would, adding a low-E storm window or panel, would then turn it into a triple low-E unit, basically. This was shown to be cost effective in climate zones 6 through 8, as well as the eastern part of zone 5, which has higher heating fuel costs, such as Pennsylvania and New York. In this case, the savings to investment ratio, or SIR, ranged from 1.1 to 1.9. And again, this was for natural gas heating, and if you do it with propane or electrical resistance heating, then they're recommended over a much larger range because those are higher cost fuels. So taking these really positive results, both the field studies and some of the weatherization and climate-based modeling we did, one group we're working with now is the Consortium for Energy Efficiency, or CEE, which includes a lot of utilities and energy efficiency program administrators, and they have formed a Windows working group together between CEE members as well as industry stakeholders to see how can we advance the uptake of efficient fenestration products across the U.S. and Canada, both efficient new and replacement windows as well as window attachments such as low-E storm windows. One of the first outcomes of this group was the CEE window product overviews published in February as a resource for CEE members and energy efficient program managers that really goes into detail about each of the options and technologies for addressing windows in a utility or energy saving program. And then the next step, there's currently a couple different working groups. There's one Windows attachment subgroup that includes low-E storm windows, and in fact our next meeting will be in Salt Lake City as part of their industry partnership meetings, September 17th and 18th. Now, we wanted to add a slide in here about code compliance and some of the questions we get about how the code requirements apply to low-E storm windows and panels. Now, in general, for the energy code, storm windows are already specifically exempted from the energy code because you're improving the energy performance of what's already there. So that's a good thing, and the code recognizes that. As for other building code requirements, such as structural and wind load and fire resistance requirements, those are generally going to be met by the primary window and building facade. So generally, it's not a concern as long as the low-E storm window or panel is not somehow adversely impacting that performance. So really the main thing you have to keep an eye out for when using Lowy storm windows or panels is to check if any of the storm windows will be used in a hazardous location defined by the building code. So for instance, an interior panel installed near a bathtub or near a swimming pool, those kinds of scenarios that are defined in the building code that then require tempered safety glazing. Very easily done. You just need to specify tempered glass for that application. Next question we get a lot is, do I have to file for a permit? And that really comes down to the local jurisdiction. And our experience is that, installing these panels and storm windows can be a do-it-yourself type project for a homeowner, or you can have a contractor do it. But because of that scenario, most jurisdictions generally do not require a permit to install Lowy storm windows, but you always need to check with your local building department. It's really a local issue you need to check. Third question we get is, should I check with my homeowners association before installing Lowy storm windows? And the answer there is yes. Just like any other modifications to the exterior of the home, whether you're installing a mailbox or want to paint your house, you need to check and see if your particular neighborhood or HOA has any covenants. In general, they should approve it if they're looking at modern Lowy storm windows. As we noted, they're very aesthetically pleasing. They're made to design to fit in with the architecture of the building. And in fact, Lowy storm windows are often preferred in historic preservation programs for preserving and the appearance of the product. But if it is a concern or an issue, you can also consider interior panels, interior Lowy panels. So couple of last items looking to the future before I hand it off to Sarah. Some of the other activities going forward. Recently, Lowy storm windows were integrated into the FEDS model, which then supports their use in most federal building energy audits. DOE is supporting the development of a new organization and certification and rating program for window attachments, and that work will be going forward and covers a wide range of products, including storm windows. As I mentioned, we're working with CEE to develop the tools and resources for energy efficiency incentive programs. And we're also working directly with utility and weatherization programs to provide technical assistance. So contact one of, Catherine Court's kind of the lead on this for PNNL, or you can contact myself and Sarah Witter, and there's other people on the call. I know Carrie Haglund has been working with a group up in Minnesota, also goes by the acronym CEE, but a different group. There's a lot of work out there. Contact one of us for a lot more details. So next, I'll hand it over to Sarah Witter. Sarah is a engineer at Pacific Northwest National Laboratory, and she's a expert and worked in a wide range of areas related to energy efficiency of homes and buildings. Not just windows, but all components of housing and the Building America program. And in particular, she's an expert on the side-by-side test homes that are at PNNL, and today she'll be talking about some of the results there with Lowy storm windows.
Thanks, Tom, and good morning or afternoon, everyone. As Tom said, I'm Sarah Witter. I'm an engineer at Pacific Northwest National Laboratory, and I'm going to talk a little bit about some testing we did of Lowy storm windows in the PNNL lab homes. And the lab homes are a great expansion of some of the case studies and lab studies that Tom discussed previously in the presentation, because it's sort of a compromise between lab testing and full-on field testing. We get a lot more precision in our answer in the lab homes than we can in a field study, because we simulate occupancy and we mitigate against a lot of the confounding factors that you'll see in field experiments. But we can look at the whole house energy performance, which is not always possible in a lab. So with that, I'll get into it. Let me move forward here. Okay, so before I dive into the results, I did want to acknowledge just a lot of supporters of the lab homes work. The lab homes have been on the Richland campus here at PNNL for 3 years now, and it wouldn't be possible with all these supporters. DOE has different agencies within DOE groups within DOE have donated a lot or supported a lot of research there. Bonneville Power Administration here in the region, the City of Richland, we've been working with them to supply power to the homes and also around the things that they want to see developed for the city locally here in terms of energy efficiency measures, and then also some other more regional local collaborators. I also wanted to just acknowledge the climate that this testing was done in. Tom talked a lot about the where low storm windows are cost effective, and here in Richland, Washington, in Climate Zone 5, they, based on the modeling, they certainly should be cost effective, and then this was just sort of validating some of the modeling that Tom had discussed previously. So we're in the southeastern part of Washington. Just for those that aren't familiar, it's the desert out here, as you can see by the picture. And so we get really hot summers and then really cold winters. And we measured the low east storm window performance both in the summer period and the winter period. So the lab home characteristics, we have 2 manufactured homes that were provided by Marlette, which is a manufactured housing manufacturer in Hermiston, Oregon. And that was a really cost-effective way to get 2 pretty identical homes. We specified them a little bit different than Marlette typically produces homes, so that they would be representative of more of a 1970s era housing stock that we see typically here in the Pacific Northwest region. So you can see it has down-specified insulation levels, R22 in the floors and the ceiling, and then R11 in the walls. And then I've highlighted here one thing that stands out for this experiment and the first experiment we did in the lab homes, looking at the performance of highly insulating triple pane windows. We have a significant amount of window area in the homes, and that allows us to, in a way, exaggerate the benefit or the impact of these window technologies and get a better signal. This is just the floor plan of the lab homes. You can see how it's laid out. It looks like a typical home, 3 bedrooms, a master bath, and a regular bath. And then I just point out these up is south, so converse to what you might think. And you can see that we have a sliding glass door facing south and then some significant west-facing glass in the dining and living room, which is also beneficial for examining how low east storm window or the highly insulating windows can improve comfort in the home, especially with setting sun, that afternoon heat that we experience in the summertime. These homes are also highly monitored and controlled, and that's what gives us such a precise measurement at the end of these experiments that we do. We have commercial lighting panels as the circuit panels in the homes. So we have 42 individually monitored breakers, so we can measure uniquely almost every load in the home. And half of them are controllable, which is how we simulate occupancy in the home. We turn on and off lighting, we turn on and off some of the appliances, and generate sensible loads within the home that are representative of people and equipment, so that we have identical occupancy patterns that are representative of a typical occupant in both the homes. And I know that there's a lot of variability in occupancy patterns, and we could have an entire webinar about that, but in these homes, it's really the really nice thing about the way the homes are laid out is as long as we do it identically in both the homes, it sort of becomes a null factor, and so it's not as important that we get the occupancy itself exactly correct as long as it's identical in both the homes. We also have temperature and relative humidity monitors throughout the home for ambient air temperature and comfort measurement within the home. We have a mean radiant temperature sensor, which is that black ball that's in the second picture down, and that measures sort of what what a person would feel like, what the temperature next to the window feels like. It's meant to help us measure comfort. And then we also have interior and exterior surface glass temperature measurements so we can look at conduction through the glass. And we take all our data with Campbell Scientific Data Loggers. We typically do our analysis with the 1-minute data, but we collect it on a couple different intervals. So I've talked a little bit about how the lab homes are unique. The main thing that makes this platform unique is that it has a built-in control. So we have one home that has baseline windows, and in this case, we'll talk about that later, but it's a clear glass, aluminum frame, double pane windows, and then another home that is identical in every way except for the one technology we're trying to evaluate. And that allows us to precisely look at the impacts associated with that technology, and gets us a lot more causal answer than you can get in field studies. But that's dependent on how identical the homes are. We're assuming that these homes are operating the same. And so when the homes were first sited, we did an initial building construction comparison to verify similar performance, and the homes operated pretty much were as similar as you could expect, and actually a lot more similar than you would get with site-built, stick-built housing because they were manufactured homes. And then before each experiment, we also do an active baseline or a null test, where we, before the technology is retrofit, will operate both the homes for about a week with full occupancy and HVAC control, just to ensure similar energy performance before we do the retrofit. And then anything we see that is varying from that baseline performance, we can attribute to that retrofitted technology. So let's get into the experiment now. So here's a description of the window characteristics. The baseline windows I described were a double pane clear glass window with aluminum frame, which we have a lot of in the Pacific Northwest region for these unretrofit sort of 60s, 70s era ranch homes. You can see the U factor, which is a measure of thermal resistance, the solar heat gain coefficient, which is a measure of how much solar heat will come through the window and get into the house, which is beneficial in the heating season, not so great in the cooling season. And then the visible transmittance, VT, is how easy it is to see through the glass. So you can see we had a significant reduction in U factor and solar heat gain coefficient with the low E storm windows. I will mention that these numbers for the low E storm windows, 0.33 and 0.53, and then the patio doors as well, were generated via modeling that was done by a company using LBNL's Window Therm model. They are created in accordance with the NFRC testing techniques, but there's not official NFRC certified ratings available for low E storm windows right now, which is one of the, or other window attachments, which is one of the barriers to really getting these technologies incentivized in the market, is we don't have a really clear way to describe their performance in comparison to other window fenestration products. And then I compared the performance we're seeing from the baseline windows with these exterior low E storm windows attached to the highly insulating primary windows that we retrofit in our first lab homes experiment. You can see we got a little bit better U factor or thermal resistance performance, and significantly reduced solar heat gain coefficient, because those had 2 low E coats, which would be great in the Southwest in a heating dominated climate that did limit our heating season savings. So I'm not going to spend that much time on this slide. Tom covered in great detail how low E storm windows save energy. This is just 3 visual depictions of it. Just like a double pane window, they're creating an additional dead air gap that will decrease conduction. There's also, it'll reflect heat back into the space and can decrease air leakage. I am going to spend a little bit of time on how Lowy storm windows are installed. The Lowy storm windows are very easy to install. These are all the tools that are needed. So any homeowner or can do it who's handy with, a screwdriver and a measuring tape. Window contractors or even general contractors can also easily install Lowy storm windows. This isn't a complicated technology to install. You just need caulk and a caulking gun, something to clean up the caulk. A screwdriver or a screw gun will make this even easier. And then measuring tape is probably the most important, actually, piece. The first step to specifying and installing storm windows is measuring your existing window opening. And this is really probably the most important step to make sure your windows will fit properly over your existing primary window. This is applicable for both interior and exterior Lowy storm windows. Exterior Lowy storm windows can be installed in two different configurations, either an overlap installation, which is what we did in the lab homes, and we'll see some pictures of that later, or a blind stop configuration where it fits into the window opening. And then once you have your manufacturers typically have specific instructions for the dimensions that they're looking for, and so follow manufacturer instructions. And then windows can be custom ordered from window distributors or some big box retailers. And there's also some common sizes that are available that you can purchase off the shelf. So measure, measure, measure. Typically for a slider or for any horizontal window opening, you'll want to measure the top, the middle, and the bottom, and then make sure you use the smallest measurement so that your window will fit into the window opening. For an external installation, I mentioned this is the blind stop installation type. You first want to dry fit the window, so hold the exterior window up to the window opening and make sure the screw holes are all landing on solid wood. You want to make sure that the storm window and the primary window both open in the same direction. That'll make it easier to use and increase the permanence of the installation. Then just take the window down, caulk around the opening, put the window back in place, and then screw in. You only want to caulk along the top and sides of the window opening. Don't caulk the bottom. Exterior storm windows have weep holes designed into the bottom. They have a little sort of plastic gasket on the bottom to help make sure that bottom edge is as airtight as we need it. But those windows will help with drainage if any condensation should occur between the primary window and the exterior window. For an interior installation, the process is very similar. Interior windows are only available in the blind stop installation type, and so you'll typically have a trim piece that'll go between the primary window and the interior Lowy storm window to make sure that you have a good thermal break between the two windows and a sufficient gap. You can see in the upper right-hand corner, we're pointing to the screw holes that will be in the Lowy storm window frame for an interior window in a blind stop installation. You can see the contractor installing it in the lower left window, and you also want to make sure that your low-E coating is facing the right side for both interior and exterior installations. And you can do that. Sometimes the manufacturers will put stickers on them, but they also feel different. So you can sort of rub both sides of the window, and the side with the low-E coating, it's a pyrolytic coating, and it feels squeaky. If you run your fingers on it, it'll squeak, and it just has higher friction to it. The Lowy storm windows don't have weep holes, so you want to caulk around the whole opening, and because they're meant to be the primary air barrier. And so if condensation, particularly from inside generated moisture, is a concern, an interior Lowy storm window might be something to consider. So there's a lot more details and instructions on how to install Lowy storm windows. We made a YouTube video. There's a link there that describes this whole process. There's more detailed instructions on the Building America Solution Center, so there's a link there, and then also there's information on at the Efficient Window Coverings website, which has a lot of great information about efficient windows in general. So the results from our Lab Homes experiment, we saw an average of 10% whole house energy savings from the Lowy storm windows, compared to 12% from the R5 triple pane windows. And that's really significant savings from a pretty cost-effective technology. I've showed just the average daily energy savings here. Those are extrapolated from our seasonal measurements using, just a heating degree day extrapolation. We've also generated some energy models to corroborate those numbers using Energy Plus, but these are just the heating day regressions. And you can see we saw, for the Lowy storm windows, we saw better savings during the heating season, the winter, than the summer. That was the opposite in the highly insulating window experiment. We saw better savings in the summer because of the low solar heat gain coefficient. We also measured the air leakage performance of the Lowy storm windows, and we did some sensitivity blower door testing, which is what's shown in the table, to try to figure out which window was our primary air barrier for the Lab Homes experiment. And for us, the primary windows in the manufactured housing in general has a reputation for being pretty airtight, because there's a lot better quality assurance that can be done on a manufacturing floor than out in the field when you're building a stick-built house. And so these primary windows it's a new manufactured house. They were pretty tight, and they were our primary air barrier. So those energy savings numbers we saw before, 10%, could probably be improved, since those are really just from the improved thermal performance of the Lowy storm windows. We're not really getting a lot of benefit from from decreased air leakage in our experiment, which probably wouldn't be the case in the field. This table, I'll just spend a little bit of time describing it. Lab Home A, that first line that's italicized, is just showing the comparison of it's just for a baseline. That's our unmodified home, and so we're just showing how similar Lab Home A and Lab Home B are. You can compare that first line to the second line, where both the primary window and the storm window are closed, and we did not seal the bottom edge of the storm window. So some people have asked, well, don't the weep holes, decrease the benefit that you might get from decreased air leakage from a Lowy storm window, because it's not as airtight as possible? And that's, of course, not why the weep holes are there. They're there for condensation, but we did do some experiments to try to seal that bottom edge and see if it improved the air leakage performance, and from our testing, it didn't at all, and or not in a significant way within the accuracy of the blower door, and that's due to the design of the weep holes. They're designed to prevent air leakage into that dead air space, because they're both at the bottom and they don't have an escape at the top. So the other thing I'll mention about the energy savings performance that we saw in the Lab Homes for the Lowy storm windows is that for the heating season, the majority of the savings occurred on sunny days at night, when it was the coldest outside. And so you can see that in the graph on the left. The blue line is Lab Home A, which has the baseline windows. The red line is Lab Home B, which has the Lowy storm windows. And then we're also seeing the outdoor temperature on the right axis and the dotted line. you can see there's a more difference between the red and blue line in the morning before the sun has risen, and then it separates again in the evening. On this sunny day, we didn't see a lot of savings in the middle of the day. If it was cloudy, we have graphs of similar to this on cloudy days. We see that difference maintained throughout the day. And then in the graph on the right, this is the summertime, and so you can see the maximum amount of savings is achieved in the afternoon period when it's the sunniest and the hottest. And so we just wanted to note that that is coincident with a lot of peak power periods that utilities experience. And so similar to a lot of efficiency or shell measures, this can also be a way of decreasing some of that peak energy use in the summertime. Tom talked a lot about the cost effectiveness of storm windows. This is just the results we generated from our specific Lab Homes experiment. I have a couple costs that we used for Lowy storm windows, a low cost, a medium cost, and a high cost, and this was just based on installation data and how much we got the windows for, and just general cost information about Lowy storm windows. The total installed cost was between $1,500 and $2,000, a little less than $2,000 for the Lab Homes, and then that annual savings number is based on the heating degree day regression that I mentioned earlier. And so we have a simple payback period of between 5 and 7 years for these homes. And then I have in the bottom there compared to the R5 windows, which were $6,500, $7,000, had a little bit better savings, but that results in a simple payback period of upwards of 20 years. And it's not that replacing your windows is an excellent idea, but people replace windows for a lot of reasons that are typically not tied to payback or energy savings. For health and safety reasons, a lot of times for aesthetics or improvement of home value. Sometimes people do it for comfort reasons, but it's typically not driven by an energy or cost effectiveness calculation. So if we're looking at cost effective retrofit solutions for low income or any type of residence, Lowy storm windows are a really great retrofit technology when window replacement is not already being considered for another reason. As Tom mentioned, these are the references that have been cited throughout the presentation, both Tom's and mine. So there's some links there to some of the specific reports, and then just the citation information, so you can look it up on your own if you want more information. There's also many of those reports and a lot of other information is available on the Building America Solution Center. For those of you that aren't familiar, Building America Solution Center is a sort of a database of energy efficient home construction techniques and technologies. It provides really specific installation guidance, including climate-specific recommendations, code requirement information. It has videos and CAD drawings. It's a really great resource for utility programs, for builders, for contractors, on how to properly install technologies that can help decrease energy use in homes. And with that, I think we've been presenting for about an hour here. I don't know how many questions we have, but I think I'm going to turn it back over to Pam, and we can maybe field some questions if there are any. So thank you all for your time and attention.
Thanks, Sarah. That was great. Yeah, we did get some questions coming in, and if you still have questions, please go ahead and type them in the question pane. Tom, I think I'm going to turn it over to you, and I'm going to give you a couple questions that you could answer, and then I have some for Sarah as well, or you guys could tag team. So one of the questions that came in was some technology-specific questions regarding the SASH. So could you provide some more information, Tom, on the sash, and is it metal, and is it thermally broken, and does it make a difference?
Yeah, so of course you can really use any material in these products, but the vast majority of them are all aluminum. Usually, a durable painted aluminum, so it can come in any color, but the sash frame itself is also aluminum. But I think the question is asking about whether it needs to be thermally broken or not, and the way a Lowy storm window is installed, either on the outside or the inside, is there is a thermal break there between the storm window and the primary window. That's either on the wood brick mold on the outside, or on the inside you have the surrounding sill. You're not attaching it right to the primary window, or there's some cases a wood blind stop in there as well that creates a thermal break. So really, in the end, the material of the sash itself doesn't matter, other than, I guess, from a structural or aesthetic standpoint, but there's no thermal bridge there.
So which really leads into another question, Tom, and it has to do, is there a recommended air gap for spacing?
In terms of performance, you generally probably want a half-inch or more. You can generate these charts that look at the U factor as a function of your airspace, but it's pretty flat. It's pretty stable for an air gap once you're about a half-inch or greater. You just don't, if you're really at like a quarter-inch, then that might be a little too tight, and it's still better than nothing, but it's not going to be as high performance. In reality, though, you're usually limited by the geometry of the window opening and the sill and everything around it, and so most are going to be somewhere between anywhere from a half-inch to several inches, but it's not real sensitive at that point.
Okay. Another question that came in is, will they work with a hopper or awning type windows?
Yes, although you have to, I guess, it depends on the type of the product. So if you have a casement or an awning or a hopper or any sort of projecting product that projects outward, then you would want to put an interior Lowy panel over that. And there are both fixed, but there, of course, the whole point is you want to be able to open and ventilate it. So there's also operable interior panels that you would then put over there where you can open the sash and then operate the projecting unit. If it happens to be a project-in casement, they're not as common, but they do exist, then you would want to put on an exterior panel. So you can do it, you just have to, it may then restrict whether you use an interior or exterior panel.
Okay. Two questions regarding solar. On a double pane film, on the outside pane is it for the outside pane for solar control? And then the other solar question is, how is solar control Lowy different on storms?
Yeah, so to do a Lowy storm window, you have to have a durable Lowy coating, because it's, even though it's kind of somewhat protected, it's still going to see the elements and humidity and moisture and all that. And so you're a little more restricted on the types of coatings than you are in a sealed insulated glass unit in a new window. So the vast majority of these, there's coatings from all different companies, but are a high solar gain, clear, Lowy. But there are products available that are a solar control, pyrolytic, durable Lowy that can be used. And in terms, and you would only use, just like I think one of the questioners pointed out, you want the solar control layer to be to the outside. So you only use those products on exterior Lowy storm windows. And this is very good for climate zone 3, for, if you know that, that's, Georgia, the Carolinas, across kind of that southern, south central U.S. And in terms of performance numbers, you can estimate the U factor and solar heat gain over different types of primary windows, and over a single pane wood window, for instance, very common. A regular Lowy storm window, they'll both have a U factor that ends up around like 0.34 or so. The solar heat gain for a regular Lowy storm window might be between, 0.45 up to 5.0. With the solar control glass, you'll be down around 0.35 to 3.7, somewhere in that range.
Okay, great. Another question, this is regarding condensation. Are there condensation issues installing a double pane storm with double pane windows? And, I could address this to Tom, or Sarah could easily answer this question.
Well, I'm not sure what they mean by double pane storm window. These are usually a single layer of low E glass, or you can use other materials over the thing, whether you put it over a single pane window or a double pane window. I guess the way you think about condensation is whatever is most to the interior of the home, you want to be tight. So, because you don't want that warm, moist, humid air from the home to leak out and then hit the cold outer surface. So, if you're putting in an interior panel, those are designed to be very airtight, and so it stops that warm, moist air from leaking through and hitting the primary window. So they're very good for condensation issues to begin with. If you're doing an exterior window, in practice, you want to seal the existing window as best you can, make sure the weather stripping's in good shape, but that's also the reason we have weep holes in exterior storm windows, not just to let any liquid moisture get out if there happens to be any in there, but also to help with any condensation issues. Sarah, did you have anything else to add to that? Or?
No, that's the same thing I would have said. Just like I mentioned in my presentation, I think if condensation is really a concern in the particular home, because the ability to seal the primary window is an issue, or you don't think you can effectively seal the primary window, then you just might want to consider interior storm windows, because you can make sure that the primary, as Tom said, you can make sure the primary air barrier is on the inside window, whether that's your low E storm window or your primary window.
Okay, I have two questions regarding the NEAT modeling. First one is, why is NEAT used instead of the Building America BOPT? And then, how are low E storms been tested in the NEAT version 8.9? Now, there's not been an option for the low E storm windows, only the low E windows. Again, this has to do with the NEAT modeling.
Yep, and I know exactly what they're talking about, because there's a little trick, and I actually have a little presentation that I can email to the person. But NEAT added the ability to include low E storm windows back in 2009. I think you have to have version 8.6 or later, or maybe 8.5 or later. But when you look at it, there's storm windows, and its default is a clear storm window. And then you go into the setup library, and you change the property of that storm window to make it a low E storm window. You plug in the emittance for that, the glass used in that storm window, which for all these products, the number is 0.16. But we can email the questioner or anyone else a few of the slides on how do you actually model low E storm windows in NEAT. Regarding the question of why did we use NEAT instead of BOPT, it's mainly because we were targeting that initial analysis at state weatherization programs, such as what we did in Pennsylvania, and there they use NEAT as a standard tool to calculate the savings investment ratio. But presumably you would come up with similar results in BOPT as long as you get the right properties in there.
Okay. This has to do with CRAFT certification. Is Building America developing a performance standard benchmark for the U factor or solar heat gain coefficient or infiltration?
Building America is not, although hopefully they will participate in the process. But DOE has set aside funding, and now it went out to a bid. There's a new group. Pam mentioned CRAFT. It's an acronym, but basically it's a new organization that will be developing a standardized certification and rating program for all fenestration attachments. So blinds, shades, solar screens, window film, anything you can think of, including low E storm windows. So that effort just started right now. I think it's starting this fall, where they'll be developing that program. In the meantime, you can estimate U factor and solar heat gain using Windows 6 and Therm6 software tools that are out there, so you can estimate it, but there's not really an official certification program yet, like Sarah mentioned.
Okay.
So it's coming, though.
We'll just address a couple more questions, and then questions that we don't get to, we have captured them with your name, and we can address them later offline to you. So another one on climate-based modeling. Have the storm windows been tested in climate zones 1 and 2 with a perforated screen, such as an inflector or ecoflector?
So what we modeled we did include some analysis in zones 1 and 2, no field studies or anything, just the calculation analysis. But we were doing both we're doing the glowy glass storm windows with the high and the solar control glass. And while we found energy savings in climate zones 1 and 2, it was highly dependent on the home type, and the payback period could range over a wide range, so we kind of did not include that. What we said for our recommendation is it needs to be studied on a case-by-case basis. I think what the questioner is asking is, well, can you incorporate this with some sort of like solar screen where you have both the benefits of a low E storm window or panel along with a solar screen or other screen? We did not test that, but I have a feeling that would turn out rather well in that climate zone.
Okay. Question on cost effectiveness. Since these products have a neat cost effectiveness of greater than one, do you expect them to be cost effective for energy efficiency programs according to cost effective tests?
Yes, and that was exactly the point of this paper that we did with PNNL, where the climate-based modeling, where we looked at 22 different cities to calculate that SIR, and then we also used ResFin just as a second method as well to look at cost effectiveness, and for that one I think we looked at a return on investment between 7 and 10%. But that's where those maps showing the recommended ranges are. In those areas, when we tested across 39 different home types, it was always proven to be cost effective. So yes, I guess you need to look at your particular area, but that data may be there already to show that where you are, whoever the questioner is, that it would be cost effective for a local incentive program or energy efficiency program.
Okay, let's end it with the last question regarding compliance. So are building permits required anywhere that you know of to install these low E storm windows? Sarah, you want to end with answering it?
I don't know. Tom might be able to answer it better than I can. I think it'll be very jurisdictional, as all codes are, but I'm not familiar with where you would need a permit with an exterior storm window, since you're changing the appearance of your house. You might have to talk to your homeowners association, but I don't know that a permit would be required because you're not changing the structural performance of your house. Tom, do you want to correct that or have anything else to add?
No, I think that's about right. It's going to be, you need to check with your local jurisdiction, but just in a general sense, I've not heard of many cases requiring a permit, but it's very locally dependent. One place you may want to look at it is if it's part of a bigger building energy retrofit. For instance, some of those photos, that were not just single-family homes, but doing a large building where they're doing a complete renovation of mechanical systems and so forth. I think they included retrofitting the windows as part of the permit. But if you're talking about a single-family home, I think that's right. It's check with your local jurisdiction, but generally you're not going to need it, I don't think.
Okay, thank you, Tom and Sarah. That was a great presentation. We will be posting the actual presentation in PDF format and the recording of this webinar today. If you have additional questions, the contacts for Tom and Sarah were up here, as well as the program coordinator for the Low E Storms, Katie Court. Thank you again. We would like to end this webinar, and thank you.